we have our 1-bit adder, so a circuit capable to add up a number of 1 bit, 2 numbers of 1 bit each, plus a carry. And now we want to build a circuit to add 4-bit numbers. So to do this, we add a circuit here, and I call it adder 4 bits. And in this circuit, I'm going to drag 4 single-bit adders. 1, 2, 3, 4. So the idea is this one. Each circuit adds 2-bit and generates a carryout, and this carryout should be connected to the carry-in of the next adder. So this adder, for example, adds the 2 least significant bits of our 4 bits number, and the carry generated from this addition is goes in input to the next adder, and so the next carry out from this adder goes in input to the next one, and so in this way the carry propagates from the least significant bit toward the most significant bit. And this is our idea, but you see the position of input and output pin in our circuit is not ideal to connect them, because we have to do many crisscrossing of wires if I want, for example, connect this one to this one. And the best thing to do is to modify the layout of our circuit. So I click here, edit, view the circuit, subcircuit appearance, and I want to drag our A and B in this position. This is A, this is B. So these are the 2 bits we want to sum up. This should be the carry in. So the carry in goes in this position, and this is the carry out, which goes here, and this is the sum, which goes here. So you see, it's some pins goes outside the shape of the circuit, and I can correct this little error in this way, dragging the 2 sides of our circuit. And so here we have our new adder, and I go back to our circuit, main circuit, and drag a full adder 1. So now you see here we have a carry out and carry in, and another one, 1, 2, 3, and 4. And now it is easy to connect the carry out to the carry in of the next adder, the carry out to the carry in of the next one, and finally this one to this one. But now there is a little problem, because the first adder, the adder which sums the 2 least significant bits of our 2 numbers, the first adder doesn't have any carry in. So we have to input this adder with 0, because when we add the first 2 bits, the least significant, so the rightmost bit, we don't have any carry from any other adder. So here we have to put in input the value 0, and of course we can do this in this way, but it's better to use a constant here. I now explain you the difference. The constant is this one in Logisim. I don't want the value 1, I want value 0, so I have to modify the property of this pin, and so here I write 0. Don't worry about this notation 0x0 because this is how Logisim notates hexadecimal number, but this is 0. Okay, I orientate this one in downward position, and so, or better in this way. So now I can connect 0 to the carry input of this adder. So why I use this constant and not a normal input pin? The reason is because an input pin loses its value when you close Logisim. So basically an input pin purpose is to input a value and not to store a constant value. Here we want to have 0 always in every possible circumstances. So and when I close Logisim, I want to store the value 0. I don't want to change this value. So now I have to fetch each adder with a bit. We have two different numbers, A and B, and each of these numbers consists of 4 bits. So let me show you. And now I want to use a splitter, two splitter, to group together these 4 bits representing A0, A1, A2, A3. So the 3 bits or 4 bits, sorry, of number A, and B0, B1, B2, B3, which are the 3 bits of number B. So I use 2 splitters. And you see, okay, bit 0, bit 1, bit 2, and another one. So I'm going to drag this one a bit in the best position, here down. So here I connect 2 input pins, 4-bit input pins. One here representing number A, and one here representing number B. And now in the same way I want to display the result, which is a sum represented by 4 bits, using another splitter and an output pin in this way. And finally, I connect an output pin, 4 output pin, an output pin and 4 bits here, and these are sum. So now we can try our adder. Here we have 2 numbers, A, B, so this is 0 and this is 0, of course, and the sum is 0, 2, and if I try to sum 0 plus 1, the sum is 1, this is not really interesting, but if I try to sum 1 plus 1, the sum is 2. Let me show you in this way. I connect a display here. Okay. And maybe also to display here and here. So you can better see what we are doing. 1 plus 1 makes 2, of course. 1 plus 3 makes 4, plus 7 make 8, and so on. And you see how it works. It sums these 2 bits, which, for example, are the least significant bit, so bit 0 of B and bit 0 of A together, and here it produces a carry which goes to the next adder. So this adder adds up the next 2 bits plus the carry, and so on. You see, the carry propagates between one adder and the next one, and in theory we can build a summer consisting of of how many bits we want, 20, 30. We have just to connect in this way, in this cascade way, more and more single adder. And for example, if I try to add something like 9 plus 7, the result is 0, but of course this is not the true result. It is a 0 because in this case we have an overflow. Overflow because 9 plus 7 makes 16, and it is impossible to represent number 16 on this kind of display of 4 digits. And so you see here we have a carry out from the last adder, and this carry out, which is an output pin, serves to indicate an overflow. An overflow, I remember you, happens when the number of bits of the result exceeds, it's greater than the number of bits of the two adders.